Dear all, I would like to welcome you to today's webinar about freeze drying optimization. My name is Marco Muri and I'm the business area manager for formulation of BUCH in Switzerland. That means that me and my team were responsible for spray drying, encapsulation, and also freeze drying within BUCH. What I would like to talk with you today is the optimization of a freeze drying process. I would like to give you some tips and tricks, and I would like to also remove common misunderstandings about freeze drying during the next few minutes on the next few slides. Before we start with the tips and tricks and how we optimize the freeze drying process, I would like to look again at the physical foundation of freeze drying so that you have a common understanding of how freeze drying is working. For that, we can look at the phase diagram of water, which you can see in this slide. What you can see is the triple point of water, the red dot more or less in the center of the diagram, which is the point where water is available as a liquid, as a solid, and in gas form at the same time. And this is at about 6.11 millibar and 0 degrees in temperature. Now in freeze drying, what we want to do is we want to sublimate. So we want to turn water from its solid phase as ice into water vapor. And how we can achieve that is by reducing the pressure and reducing, therefore, also the temperature of the sample to a lower level. That this can happen, the conditions need to be below the triple point of water, so the pressure definitely needs to be below 6 millibars and the temperature then will be below or will be at 0 degrees or lower. This is a process that is happening at rather cold temperatures, but still there's a common misunderstanding. Even though it happens at low temperatures, it consumes quite a lot of energy to sublimate ice into water vapor. So 1 gram of ice to be sublimated consumes about 2,800 joules of energy, which is quite a lot and which somehow needs to be supplied to the system. And this is something we will have a look on at a further slide. The most important parameter when freeze drying is the pressure. The pressure in the chamber will define the temperature of the sample. Now this table you can see below is for water. So if the sample is not heated, what we will see if we go to a pressure of 6.11 millibar, which is the triple point of water again, we see that the temperature of the sample will be at around 0 degrees. Now, usually formulations we're using for freeze drying are not frozen at 0 degrees because it's not pure water. There are some additives in, there's some APIs in, and so on. So the freezing point is typically lower. Typically it's minus 20 degrees or even lower, which means we work at the pressure of 1 millibar or lower. What you can see now is the lower you go in your pressure, the lower the sample temperature will be. So we can start at about minus 20 and we can go down to about minus 50, minus 60 degrees in sample temperature, depending on the pressure we are using. Of course, we need to make sure that the pressure is low enough that our sample will not start to melt. So make sure it definitely is well below its freezing point. But now what's very important in freeze drying and what is actually making the process moving is the difference of the temperature of the sample and the condenser. In freeze drying, we have the samples on top in the sample chamber. They are there frozen. We apply vacuum and water vapor will be removed from the samples and will be moving down to the condensers. Of course, also certain solvent vapors can be removed. But now that this vapor is moving down to the condenser, which has a very low temperature, we need a difference between the sample temperature and the condenser temperature. And this will then create kind of a suction of the vapor towards the condenser. So now if we look at the freeze dryers, our L200 on the right-hand side and the L300 on the left-hand side. The L200 has a condenser temperature of minus 55 degrees, whilst the L300 goes lower at minus 105 degrees. Now, to make sure that our process is running properly, we need to make sure that we have a temperature difference of at least about 15 to 20 degrees between sample and condenser. Now, as an example, if we use a sample at 0.7 millibars pressure, we will have a sample temperature of about minus 24 degrees with an aqueous sample. Now, if we use this in an L200, we will have a temperature difference of 30 degrees, which is very fine, more than enough, and the process will run properly. For the L300, it is absolutely no issue. We have plenty of temperature difference and the process will be rather fast. But now if we go back and look at this table, there's a common misunderstanding where the expectation is that the lower the pressure is in a freeze dryer, the faster the freeze drying process will be. And this is not correct. Because what is happening, if you go for lower pressure, you will go for a lower sample temperature. And if you go too low, for example, if you go to minus 50 degrees, and this is what a freeze dryer roughly will achieve if you just pull full vacuum on it, then you will end up with a sample temperature of about minus 50 degrees or even lower, and you will have not enough temperature difference to have the freeze drying process running properly. So that's why for aqueous samples, typically a freeze drying pressure of about 0.7, 0.6 millibars, a bit depending on the freezing temperature of the sample, is used. So like that, you can make sure you have enough temperature difference and you will freeze dry quick enough. As I mentioned, the freeze drying process consumes quite a bit of energy. It takes about 2,800 joules to sublimate 1 gram of ice. This energy can be provided in different ways. In the picture, we see two ways of how we can present a sample to a freeze dry. First, and very often used, is the freeze drying vial on a heatable shelf. With this system, we have two ways, or basically three ways, how we can supply the energy to the vial or the sample. First, A is conduction by the heatable shelf. So we heat the shelf and parts of the energy will be transferred to the sample and it will be heated up. But then we also have the radiation, C, from the top shelf, which is also transferred to the sample. And then we will have convection, B, from the radiation from the outside of the freeze dryer. On the right side of the picture, you can see a manifold with a round bottom flask attached, where the sample is frozen and a shell freezer has been used, so the sample is covering the inner wall of the round bottom flask and will have a maximum surface. Here we apply the energy to the system by the environmental conditions you have in your lab. So the system will consume energy from its surrounding to heat up the sample and to deliver the energy for the sublimation. So this cannot be directly controlled, but typically works pretty well. But obviously it will work quicker on a warmer day than on a colder day. Now, if we can heat the samples only by 1 degree, the freeze drying process will already shorten by about 13%. That means that an increase of about 5 degrees will shorten the time by half, and applying enough energy to your freeze drying process can really speed up your process a lot and can be very beneficial for your freeze drying time. What is important is if you apply energy to your freeze drying sample, that you don't overdo it and that you can somehow monitor it. For that, in freeze drying vials, we typically use temperature sensors that are frozen with the sample and then connected to the instrument. It is important when you apply such a sensor to a sample that you have it in the spot where the sample will be freeze dried at the end. So in a vial, you will have it on the bottom of the vial in the center, if possible, because the freeze drying sample will freeze dry from the top to the bottom, and there will be a sublimation front somewhere on the way down to the bottom. So like this, we can make sure that we observe how our sample behaves and that it does not melt during the process, and that we can control the amount of energy we supply, especially when using heatable shelves. This is not so critical when working with manifolds, because there the amount of energy is not typically not enough to melt the sample. So now if we use heatable shelves, what we will do in the freeze drying step, or as it is called in the primary drying, we will apply energy to the frozen sample. So we take the frozen sample out of the freezer together with the shelf. It's very important that the shelf goes into the freezer as well. We will apply energy and we will make sure with the sample temperature probe that we do not reach the so-called collapse temperature. The collapse temperature is basically nothing else than the temperature where the sample is starting to partly melt. And it's important that you understand that this is not the freezing point of the sample. It is lower than the freezing point. For crystalline samples, it's typically about 20 degrees lower than the freezing point. And for amorphous samples, it's even lower. We don't want to reach this point because when the sample will start to partly melt, our nice freeze drying cake will kind of collapse. So we take the samples out, we have our sample temperature probe in, typically in the very center vial of the shelf, so the one that sits in the very center, because this is the one that will take the longest time to dry. Now, the shelf is at about minus 25 degrees when we take it out and have it in the freeze dryer and start the freeze drying process. So that's all, and therefore it's also very important that you freeze your sample to at least minus 40 degrees. Colder the better, but at least minus 40. So we place the samples in the freeze dryer and we start applying heat, and we do that with a ramp. So we start first with minus 20 degrees. We stay for a certain time at minus 20. We increase to 0 degrees over a certain time period. We stabilize the system again by leaving the temperature stable, and we increase again to 20 degrees. Now, very important is this is not a cycle you will use for every sample or that is already optimized for your sample. This is just a screening cycle to see how does your sample behave when you apply energy to it. So what we will do is we will observe the sample temperature and see how is it behaving. At what level is the sample temperature? Is it, if it's getting too high, we will need to reduce the energy. If it's staying at the very low level, we can still increase the amount of energy we supply, and we will dry our sample faster. What you will always see when we do freeze drying with heatable shelves is that we are ramping the temperature. Why is the temperature ramped? This, of course, is a screening cycle, so it's anyway ramped. It might be that your sample has the ideal temperature and you can run it on a constant temperature for a very long time, but there will be a point where you should ramp your system. The reason is, if you imagine, we take the samples out of the freezer. We have a full shelf of samples, and these samples are frozen and they're sublimating. So they're cooling down our shelf. The shelf supplies energy, which is consumed by the sample, so it cools down the shelf. Now, the longer the freeze drying process is running, the less sample or ice we will have on our shelf. And this means the lower the cooling effect will be. And this means that we will need higher temperatures to supply the same amount of energy to the system. And this is also why we see ramps in freeze drying or primary drying. If you want to further optimize your process, it's always a question, when is the freeze drying process actually finished? If you have manifold applications, it's quite simple. Once there's no more ice on the manifold or on the round bottom flask on the outside, it means the sample is no longer consuming a lot of energy from the environment and it is most probably completely dry. With vials and shelves, this is a bit more difficult, and you cannot so simply just see if the sample is dry or not. So what we offer is we offer three methods to test this, or to test the endpoint during the process and determine the endpoint automatically in the machine. The first one is the temperature difference test. The temperature difference test works very simply with sample temperature probe. Once there's no more ice in the sample and everything is sublimated, the sample will go to the same temperature as the shelf, and our software can automatically detect that, let you know that your sample is dry, or even stop the process. This is not the most precise method, mainly because it's very much reliable on how well sample temperature probe is located on the in the very center, on the very bottom of the freeze drying wire. More precise is, for example, the pressure difference test. In the pressure difference test, we are using two different pressure sensors that are connected to the drying chamber, so where the samples are located. We use a Pirani sensor and a capacitive sensor. The Pirani sensor is depending on its environment, and if there's water vapor in the chamber, which will be the case as long as the sample is sublimating, it will show a different pressure than the capacitive sensor. As soon as there's no more water vapor, so the samples are dry, both sensors will show the same pressure value, and this can be detected automatically by the software as well. And then we also have the pressure rise test, but this is only available for the L300. Here we also have a pressure sensor connected to, but only one, to the drying chamber, and we can close the valves between the drying chamber and the condenser, so that those two parts are no longer connected. In this case, the drying chamber is also not connected to the vacuum pump anymore, and we can observe now the pressure in the drying chamber. If the pressure in the drying chamber is still is rising rather quickly, then we still see some sublimation in the process and the samples are not done. If the pressure is not increasing or very slowly increasing, then this is the end point of the freeze drying process. So like this, you can find out when is your process really done, how much time do you need to dry your sample, and this will help you to optimize further cycles. Now I would like to thank you very much for your attention. I'm already at the end of our short presentation about the optimization of freeze drying. Of course, if you should have any questions about your freeze drying process, or freeze drying in general, please do not hesitate to contact your BUCH staff, and we will help you out and guide you in your freeze drying process. So now I wish you a lot of success with freeze drying and a lot of success with all your work. Um, all the best. Thank you very much. Bye bye.